Welcome to today's webinar. The topic today is new features for the design of steel connections. My name is Andreas Hörold. I'm responsible for marketing and PR in the company Dlubal Software. For instance, the German and English webinars, technical content of the website, newsletters, and so on. I will be the moderator and also the presenter today. My colleague Lukas Sühnel will support me. He works in the customer support team and he's the main responsible person for the development of our interfaces. He knows a lot about steel and steel connection design or steel joint design. And as I said, he will support me by answering your questions today. You can ask questions via that panel here. At first, I switch off my webcam that you can see the full screen. If you have a question, just press that button with the question mark, then enter your question in that field, press send, and Lukas will receive your question and he will answer you. The other way is to watch the entire webinar and then email your questions to info@dlubal.com. Okay, let's turn to the agenda today. At first, I will introduce new features in the steel joints add-on. At least these feature that we implemented since the latest webinar. It's about half a year. Then the second point is joint structure interaction. That's one of the new features. You can consider the joint stiffness, and I will show that on a practical example. And the last point is Outlook. I show you what we schedule for the future. So those are the first new features. I integrated also the component base plate for foundation block connections. I showed it already in the latest webinar, but I wanted to hint to that features also in this webinar. Then a new feature is the definition of circular board or anchor layout. I will show that on an example. I start with the carport that I presented in the latest webinar, and I would like to start with that feature there. Let's turn to RFEM. This is the model of the latest steel joints webinar. A carport made from steel, or made of steel. And we created different joints. I show you which joints. A base plate for the columns. Then rigid connections for the frames in both direction. Then the joints for the inner purlins and the outer purlins. And to show the feature with the circular bolts, I would like to change the columns, the cross section of the columns. Members, edit. So we change the section to a circular hollow section. This one. Okay. Okay. And now let's change the base plate. So at first, we change the shape of the plate to circle. and we change the diameter to 250 millimeters. So, and then the concrete block, okay, we change it a little bit, we make it larger. Okay. So then we use 5 bolts and the radius should be 100. Okay, that's all for the first feature. Let's turn back to the PowerPoint. So, and yeah, I defined it for the anchors, and the same workflow is for bolts. So next slide, next new feature, component rib. Yeah, you can define any number of longitudinal ribs on a member plate with the rib component. And yeah, that's also possible for circular hollow sections. Yeah, we turn back to RFEM. We have got a circular hollow section, and let's define ribs here. So new component. In the middle, in the second line, you can find the rib component. So then member plate is correct. And member 1 and wall is the stiffened object. Then the type of reference should be the base plate. Base plate 1 plate. Okay, you can see the rib. So, and not on both sides, but on the front side. Okay. So, and number of hinges is 5. The same number as for the anchors. So, and let's modify it a little bit. So, okay, we changed it a little bit. Okay, 20, no, that's too small, not parallel, we use inclined. So, and then we modify the ribs a little bit. 20 is okay, and 30. Okay, that looks quite good. So let's turn to another example for the component rib. So you can also see a rib here. This is the component, and here you can find the rib. And let's modify that. We create 2 ribs with another distance, -50, 100. Okay. On both sides. Yeah, a quite useful component, and it's quite new in our program. So then let's turn back to the PowerPoint slide. Limit plastic strain for welds. Yeah, you can modify that value for more secure or something like that. The standard setting is 5. Let's turn back to RFEM. I can show where you can change that. You need to select in the navigator data and steel joint design, the ultimate configurations. So you can then see here the limit plastic strain for plates and for welds. And as I said, 5% is the default value. Yeah, but you can change that if you want. So let's turn back to the slide. Next slide. And next new feature, the component stub. Yeah, it enables extension of a member via plate joint with another member. Yeah, and if you add such a component, it's not considered for the stiffness of the global model, but for the connection. So let's turn back to RFEM. The next prepared model. So you can see that node, and imagine you want to connect this horizontal member to the column with a rigid connection, but you have no space for the bolts here because of this joint. So, and therefore, we can add a stub. So double click on the joint and add a new component. You insert component at the end. So, and you can find the stub here in the third line, and you can see the stub. Okay, so then we have to define the connected member. Member 2. Then reference member is this one, the column. So then we have to define a section. We use the same section as for the horizontal beam, standardized, then HEA 200. Okay. So now we leave the length 300 millimeters. Then we define a larger thickness. Now let's change the values to increase the plate a little bit. Okay. So, and let's modify the bolts. And 16, 10.9. So, and then 75, 90. So, okay. Yeah, that's the component stub. And you can use it for this for such connections, or also for other connections. So then let's turn back to the PowerPoint slides. Yeah, next new feature, the relative placement of objects. Yeah, you can arrange objects with a relative reference to other objects. I would like to show that also in RFEM 6. I've prepared another model, this one. Okay, let's double click on the joint components. And I would like to show that on the upper plate on this plate. So, and you can see the alignment here. The origin alignment, it's the definition of the origin. And if you say, okay, that's not the rear, but the front, then there's another reference. And the object alignment, when I say not front, but rear, then the plate is below the flange. Okay, I hope you understood what I did. I move it back to the upper side. Or let's show that on another example. I decrease the plate a little bit. Ignore the balls. So, and if you want to define the plate not on the center for both, you can, for example, define the left side for both, and you can see now are at the same edge here. Okay, that's all to that component. Turn back to the PowerPoint slide. Next new feature, connection library is now in the Dlubal Center. You can define your own user-defined connections there and so on. I will show that feature later when I search for a prepared connection in that library in the last example. Then plate component with polygonal geometry shape. You can create such plates here with a polygonal shape. That's possible now. So then the new component surface contact. You can also consider frictions between two members or plates, for example. I would like to show that in RFEM 6 as well. So I prepared that example. So you can see this member has an eccentricity, and the top of this member is equal to the bottom of this member. So, and let's create a steel joint. So those are the four members. They are not ended but continuous. Okay. Then components, new component. That's the component in the last line on the right side, contact. So then let's select the components, member plate, member 1 and 3 and flange 2, the lower flange. And for this member 2 and 4, the upper flange. Okay. So, and you can also, as I said, consider a friction coefficient. Okay, that should be all to this feature. The next feature is the steel joint design on result beam, member type, and surface models. You can define result beams or surface models and consider that for your steel joint. For example, when you create openings, then you can use a surface model. Let's show that or take a look at it on the next example. So that's the example. Yeah, in this example, there's a surface model with openings. How to create such things. That's a surface model. And for the member, I created a surface model. I double click on it. So member type, surface model. Then you have to select a section. And for example, you can then define member openings, reductions, circular opening on that distance, 2 openings with that offset and that diameter. Okay, those are the openings. And that's the assigned line 22. This is this line. Okay. So, and then you can create a joint for such a node with these components. Quite easy. Okay, that's all for that new feature. The next feature is the transfer of foundation dimensions in the base plate design. At first you have to define concrete foundations in the add-on, and then you can adopt the foundation dimensions and materials in the base plate component. I would like to show that also in RFEM 6. So that's the prepared model. That's the carport. No, we turn back in the carport. So, and we define now, foundations. I have to go or turn to the base data. Then I have to switch or check the concrete foundations add-on. Okay. So, and I define foundations now. That's let me turn to the wireframe model and I switch off the joints. So, and I have to edit the nodes. So, and I have to go to the support. So, and then edit the support. So, and I check foundations. And I create a foundation, a single foundation, new. A foundation plate without reinforcement, a simple component or foundation. Geometry 0.8. I created a little bit larger that we can see the difference to the block that we created at the moment. So that's all. Soil properties. I have to create a soil layer. So sand, for example. Okay. So, okay, that's all. Now, where are foundations below the columns? So, and now we switch to the detailed model. So, and I double click on that steel joint. So, and then I turn to the components, base plate. So, and now you can check this geometry from concrete foundations, and you will see the difference when I set the check. Okay, now it's a little bit larger. Yeah, and as I said, it overtakes also the material, not only the dimensions. Okay, so then we turn back to the PowerPoint slide and to the next new feature. The contact stresses can now displayed graphically. I would like to show that also in RFEM. So I prepared that model. It's the same carport and one base plate is designed. So then I turn to the steel joint design table. So and I double click on that line. So those are the design check details. Yeah, and the most of you knows that, but yeah, the design checks are printable. For example, this design check, that's not a black box. You can print it to the printout report or directly to the printer. That's the equation from the standard. Yeah, as I said, no black box. You can calculate it by hand if you want and check that. So, and when I turn left above to the results in steel joints, and then to the result in steel joints, I can set this check contact stress. And you can see the different contact stresses here. Okay, that's all for that feature. Let's turn back to the PowerPoint slides. And we turn to the last feature for today, and I will show that on an example. Yeah, the joint structure interaction. That's the automatic consideration of the stiffness of the steel joint. It generates hinges in the global model, and you can consider the hinges in the subsequent calculations. I will show that also in RFEM 6. I have to mention that you can click on the More Information button in the PowerPoint slides, and then you turn to the website for more information. That's valid for all the features that I show today. And you can, you get an email in the next days with a link to the website with the recording and the PowerPoint slides and the models, and you will also get your attendee certificate. So let's turn to RFEM. So that's the prepared example. A steel construction, one floor. I created load transfer surfaces to apply a wind load for that area on the top of the floor and area below the floor. So then let's show the different loads, self-weight, then the imposed load. Let's switch off the surfaces for a better overview. So surfaces off. So that's the imposed load. And the different wind loads. Then the ultimate limit state design, serviceability limit state design. And I did a steel joint design. You can see the results, for example, design ratios by section. Those are the columns. Those are the horizontal beams. Oh, okay. All is good, but we have a design ratio for the serviceability for the serviceability limit state design of the columns in horizontal direction. It's slightly overloaded, but I think it's okay. Yeah, but the question is, what happens when we create a steel joint? And yeah, that's what we check now. So we create a steel joint, for example, for this node, create steel joint. So I rename it from member to column. And this member, I call it only beam. So, and we don't use that member and that member. So that's the ultimate configuration. It's okay. And that's now the new feature stiffness analysis and stiffness analysis configuration, where are different possibilities. The initial stiffness, no interaction, and this is the new feature, joint structure interaction. And if I select that, let's take a look in it. It considers the initial stiffness, and the program or the add-on generates hinges in the global model. Yeah, we take a look at it later. Okay, then members. That's okay. And we have to select for the stiffness analysis, yeah, MY, of course, yeah, but we can also check the other stiffness analysis. Okay. So, and the program will do a stiffness analysis and create member hinges on that node later. Yeah, I will show that later on the finished model. So then components. We create a new components from the library, and now it opens the Dlubal Center. You can see a large database, and you can choose between or choose different connections. You can see I have also user-defined connections here. Only these ones. Then I can deselect it. Those are the Dlubal Software templates. For example, for I sections in our case, 2 is the number of members, and we select the number 84. This one. Okay. So it takes some seconds. It has to be loaded from the library in our model. Okay. Yeah, that looks already quite good. It should be a stiff connection, with the haunch. But we will create a smaller haunch. So we have to modify it. So at first, we change that stiffener, or we create or we add a plate on the top of the column, a cup plate. So let's do it. At first, I delete the stiffener. Okay. So, and let's load a cap plate. Okay. On the top of the column, reference member is the beam. So then rectangle, not the closer, but the farther cutting plane. Okay, that looks quite good. So parallel, thickness 10 millimeters, is okay. But we have to define an offset that we can define welds here. Also on this side, -8. So that's okay. Yeah, and we only modify the welds. For the flange, we use 4 millimeters, and for the web, 3 millimeters. Okay, that's all. So then let's turn to the end plate. So we need to modify it. The reference member is the connect member beam column. That's okay. Thickness should be 15 millimeters. Then we don't use offset, but dimensions and position. 170 is okay. 260, we decrease the plate a little bit. So -8. Okay. So then M16, 10.9. Then only 3 spacing vertically. So 40, 90. So let's move it a little bit. So, and for this then 35, 65, 90. Okay. So that looks good. We use preloaded bolts. Shear plane not in thread. So, and the flange weld 4 and web weld 3. Okay. Member cut, yeah, we don't need it anymore because of the cap plate. We can delete that. Then turn to the haunch. So that's okay. We only need to modify the dimensions, 200 millimeters, then 90. Okay. So that's all okay. And the flange welds 4. Okay. Let me check it again if all is okay. Yes, okay. So we have to modify the stiffness. The location offset is 100. Okay. So, and 4 millimeters for the flange welds. That's okay. And the other stiffener, 320. Yeah, now it's on the right position. We only need to modify the flange welds. Okay, that's all for this steer joint. Plausibility check is okay. We can add the other nodes. So, okay. Okay. So all steel joints are created, and now we have to calculate our. I did the cloud calculation, calculate in the cloud. So there are different servers. You can get an email when the calculation starts and when the calculation is complete. You can see also then the file in the extranet. So I did that already, and I turned to the calculated model. So finished. So let's turn to the steel joint design. Yeah, all is calculated and all design checks are fulfilled. So, and what is new? Those are the hinges. Let's turn to the navigator data, types for members, member hinges, and you can see the generated hinges. We can also, or let's take a look at the stiffness analysis. Here you can see the values for the rotational stiffness for the moment. So, and when I click on that hinge, for example, you can, can see the diagram. Yeah, and I hope you can see the values. Those are the values for the M phi diagram. The moment is in kilonewton meter, and where meganewton meter, 12 is equal to 12,000, and 12,1600 is equal to 12.6 meganewton meter. So, and those are the hinges, and they are considered in the global model. And when I turn back to the steel design, you can see now we have larger overloading for the serviceability limit state design. Yeah, and I think you have to consider such stiffness reductions in that case, that the stiffness in the horizontal direction in that case is too large, the construction is too weak and can swing a little bit. Yeah. And now you have the possibility to consider that, such joint stiffnesses in your global model. So let's turn back to the steel joint design. I double click on the design check, and I would like to show you, it's often asked, is it a black box what the program calculates? Yeah, it isn't a black box. I will show that on the sub model. First, I will show where you can find that sub model. Yeah, and now it loads all designs. It takes a little bit. So, and as I already mentioned, you can print the design checks with the equations from the standard in the printout report. And when we turn to the results in steel joints left above, you can save left at the bottom the steel joint model, and we call it submodel. So let's turn to that submodel. I already saved that. So, and that's the submodel, and you can verify that As I mentioned, it's no black box. You can see the deflections here or deformations. And when you, for example, wants to see the members, internal forces, the normal forces for the bolts, those are bolts. You can see it's a quite complicated surface and member model. For example, those are the welds. That's a surface with a thickness of 4 millimeters. I hope you can see that. And those are rigid links. Also here, quite complicated, but that's the submodel. What the program calculates in the background. So let's take a last look on the surface stresses, equivalent stresses, for example. The highest stresses around the bolt holes. Okay, that should be all for this new feature, or for all new features. I turn back to the PowerPoint and I turn to the last point for today, the outlook. Those are the planned features, what we would like to implement in the next time. For example, when we have implemented that features, you can define anchors in the component fastener. We will implement shear lugs for base plate connections. You can see such a shear lug here. Then anchors with anchor heads. A new component spice plate will be implemented. Then the positioning of inserted plates and members will be better in the future. We will improve that. Then members with solid sections, for example, round bars, as you can see in that image here. Then we will implement hooked anchors. Then we will implement the Canadian standard, a stiffness diagram. Then there will be the possibility to export DXF files, for example, in a CAD program, that you can add dimensions and so on. We will provide a standalone solution that you can use the add-on steel joints without RFEM. Then you need to import the internal forces and so on from other programs, and then you can calculate your steel joint. So, and the last feature is a part list that we will implement in the future. Okay, that should be all for today's webinar. I hope you could see, or I could show you new features that you can use for your steel joint. It's quite more comfortable with that features. And as you can see on that slide, we will implement more useful features that you can quickly create your steel joints and calculate them. Okay, I thank you for your attention. Thanks to Lucas for answering the questions. I wish all a nice rest of the day. Bye-bye.